Our planet faces a challenge of unprecedented scale climate change. The evidence is overwhelming, from rising sea levels to extreme weather events. The primary culprit is our reliance on fossil fuels, releasing harmful greenhouse gases into the atmosphere. We must transition to a cleaner, more sustainable energy future. The scientific consensus is clear. We must act decisively to mitigate the worst effects of climate change. Fortunately, we are not without solutions. Renewable energy sources such as solar and wind have made significant strides in recent years. However, their intermittent nature poses challenges to grid stability and reliability. Nuclear energy presents a compelling solution to this energy conundrum. It offers a reliable, carbon-free alternative to fossil fuels, capable of providing baseload power that is essential for a stable electric grid. The stakes are simply too high to ignore the potential of this powerful, carbon-free energy source. The quest for clean energy has led to a surge in interest in solar and wind power. However, their intermittency poses a challenge for stable power supply. Nuclear energy steps in, offering a continuous power solution. It provides a steady stream of electricity regardless of weather. This baseload power is crucial for grid stability. Nuclear plants have a small land footprint and emit virtually no greenhouse gases. As we combat climate change, nuclear energy is a formidable ally. At the heart of every nuclear power plant lies nuclear fission. This process within the reactor core drives electricity generation. A neutron strikes the uranium nucleus, splitting it and releasing heat. This heat generates steam, driving turbines to produce electricity. The chain reaction is controlled for steady energy release. A small amount of uranium fuel produces enormous electricity. A uranium pellet contains the same energy as a ton of coal. This energy density allows for long cycles and minimal fuel. Understanding nuclear fission is essential for a clean energy future. The specter of nuclear accidents, though statistically rare, has cast a long shadow over the public perception of nuclear energy. However, it's important to recognize that the nuclear industry has made significant strides in safety and efficiency since the early days of nuclear power generation. One of the most promising advancements is the development of small modular reactors, or SMRs. These reactors are significantly smaller than traditional nuclear power plants, offering several key advantages. Their modular design allows for factory fabrication and assembly, reducing construction costs and timelines. Another groundbreaking development is the emergence of Generation 4 reactors. These reactors represent a radical departure from traditional designs, incorporating innovative features that enhance safety, sustainability, and efficiency. Beyond reactor design, the nuclear industry has also made significant progress in safety systems and operational procedures. Advanced control systems, sophisticated sensors, and rigorous training programs have all contributed to a more robust safety culture. The future of nuclear energy depends on our ability to build public confidence in the safety and reliability of this powerful technology. Section 5. Guardians of the Core Modern Safety Systems. The safety of nuclear power plants is paramount, and modern facilities are equipped with multiple layers of redundant safety systems designed to prevent accidents and mitigate their consequences should they occur. One of the most critical safety features is the reactor containment structure, a massive concrete and steel dome that encases the reactor core. Inside the containment structure, a sophisticated network of sensors constantly monitors critical parameters such as temperature, pressure, and radiation levels. This real-time data is fed into advanced control systems that can automatically adjust reactor power output or even shut down the reactor entirely if any parameters exceed predefined safety limits. In addition to these passive and active safety systems, nuclear power plants also have dedicated emergency response teams trained to handle a wide range of potential scenarios. The nuclear industry's commitment to safety is not merely a matter of compliance with regulations, it is a deeply ingrained cultural value. This collective commitment to safety is a testament to the industry's recognition that public trust is essential for the future of nuclear energy. Section 6. Beyond Waste Innovations in Nuclear Waste Management. The issue of nuclear waste has long been a topic of public concern and a focal point for opponents of nuclear energy. While the volume of waste generated by nuclear power plants is relatively small compared to other industries, it's essential to manage it safely and responsibly. One promising avenue is the development of advanced recycling technologies. Traditional nuclear reactors utilize only a small fraction of the energy potential in uranium fuel. Advanced recycling processes can reprocess spent fuel, extracting valuable materials like plutonium and uranium that can be used to fuel a new generation of reactors. Another area of innovation is the exploration of deep geological repositories. These repositories are designed to isolate nuclear waste deep underground in stable geological formations. The nuclear industry recognizes that responsible waste management is not just a technical challenge but also a societal one. Section 7. A carbon-free future, nuclear's role in decarbonization. As the world grapples with the urgent need to reduce greenhouse gas emissions, nuclear energy stands out as a powerful tool in the fight against climate change. Its ability to generate electricity without emitting carbon dioxide makes it a crucial component of any serious decarbonization strategy. Unlike fossil fuel power plants that release tons of carbon dioxide into the atmosphere, nuclear power plants operate with virtually no greenhouse gas emissions. This inherent advantage makes nuclear energy a true carbon-free source of electricity, essential for mitigating the impacts of climate change. Moreover, nuclear power plants operate continuously, providing a reliable and stable source of baseload electricity. The urgency of climate change demands that we deploy all available clean energy technologies. By embracing nuclear power as a key component of our energy mix, we can accelerate the transition to a sustainable, low-carbon future and mitigate the worst effects of climate change. Section 8. The Energy Security Imperative, Nuclear's Contribution to Stability. In an increasingly interconnected world, energy security has emerged as a paramount concern for nations around the globe. Nuclear energy, with its unique characteristics, offers a compelling solution to this multifaceted challenge. Unlike fossil fuels, which are often concentrated in geographically limited areas, uranium, the fuel for nuclear power plants, is relatively abundant and widely distributed globally. This reduces dependence on volatile international markets and geopolitical hotspots, enhancing energy independence and national security. Furthermore, nuclear power plants require only small amounts of uranium fuel to generate vast amounts of electricity, reducing the need for frequent refueling and transportation. In a world grappling with geopolitical uncertainties and the growing demand for energy, nuclear power provides a pathway to greater energy security. By embracing nuclear energy, nations can enhance their self-reliance, reduce their vulnerability to external pressures, and ensure a stable and predictable energy future for their citizens. Section 9. The Price of Power. Economic Considerations of Nuclear Energy. The economics of nuclear energy are complex and often subject to debate. While nuclear power plants have high upfront capital costs, their operating expenses are relatively low and their lifespans are long. One of the main contributors to the high initial cost of nuclear power plants is the stringent safety regulations and rigorous licensing processes involved. However, once operational, nuclear power plants have remarkably low fuel costs, as uranium is an energy-dense fuel source, and a small amount goes a long way. Moreover, nuclear power plants have long operating lifespans, typically ranging from 40 to 60 years with the potential for license extensions. The emergence of small modular reactors, or SMRs, promises to reduce upfront capital costs through factory fabrication and modular construction techniques. As we transition to a clean energy future, it is essential to consider the long-term economic benefits of nuclear power, including its stable electricity prices, job creation potential, and contribution to a more resilient and secure energy grid. Section 10. Shifting Sands, Public Perception and Nuclear Energy. Public perception of nuclear energy is shaped by historical events, media portrayals, and safety concerns. Nuclear power offers carbon-free electricity, but public trust is crucial for its acceptance. Chernobyl and Fukushima cast a long shadow over nuclear power's image. The industry has learned from these events, enhancing safety and regulations. Public education and open dialogue are essential for fostering understanding. Engaging communities and addressing concerns can build trust in nuclear energy. Section 11. A sustainable future, nuclear's place in a clean energy mix. As we chart a course towards a sustainable energy future, a diverse and flexible energy mix is essential. Nuclear energy, with its unique attributes, deserves a prominent place in this clean energy portfolio. Its carbon-free electricity generation and baseload power capabilities make it an ideal partner for renewables. Together, they can power a sustainable future.